polarization. This is buffering. Let me hit pause here real quick. Oh, it's still going. Sorry. Polarization. There it goes. All right. So I want to talk briefly about electrical polarization. This is going to be a short video. And maybe talk briefly about these terms, insulators and conductors. So you can see everything I've got here. Let's go through it. So electrical polarization, you can think of as charge separation within an object, or sometimes I like to think about it as charge reorientation. Basically, here's an object that could be polarized, and I could modify the distribution of charges within this object so that one side of it is more negative and one side is more positive, or maybe, yeah, something like that. All right. Now, before we get too much further, we're immediately going to have to discuss things like conductors versus insulators. So when you think of conductors, you probably think of things like metal. All right. So copper, aluminum are good conductors, gold, platinum, things like that. And in metals or conductors, the charges are free to travel. And by that, usually we mean electrons. So maybe I'll clarify that here. Electrons, and this is not true for all conductors, but for now, let's just assume it's only electrons. So the electrons inside a piece of metal are very free to travel around, and that makes it easy for them to separate or reorient. So they are strongly polarizable. And then when you touch a piece of metal, it's easy for it to transfer charge. And so a charge will transfer quite easily once you make contact with a piece of metal, or once the piece of metal makes contact with something else. So that's just some basics of conductors. There's a lot more to it, but for now, let's just stick with that. Insulators, on the other hand, the things that I think about are rubber, plastic, glass, things that don't conduct electricity very well. And you might be saying, are there things in between like graphite? Yeah, sure. Or semiconductors? Yes. But for now, let's just restrict ourselves to these two classes. Things like metal, which conduct very well, and they're easily or strongly polarizable. And then insulators, the charges are less free to travel. They can still move, but it's much more difficult. And so there's a strong difference here. The charge transfer is more difficult here, and this is the reasoning. Maybe if I just show you with this balloon. If I rub this side of the balloon, this side of the balloon gets charged, but the other side does not. It's because the charge is not free to move around within the surface of the object that much. Now, to be clear, right now, I want to talk about polarization. Before we talk about polarization, we typically need some sort of charged object in here. And so what's going to happen is, let's say I charge this object, I could then use this charge to polarize the wall, or to polarize, oops, where did that go? I could polarize this piece of tinsel, right? And so if I bring this close, you might notice when I bring this balloon close enough, the piece of tinsel is actually attracted. And let me see if I could. Uh-oh, did it make contact? It did. Now they're both charged. So notice once this piece of metal made contact, it was very easy to transfer some charge there. Let me try and absorb that charge onto my body here. Let's see if we can get this to be attracted again. Try and hold it in a spot where you can actually see on the board here. Oh, there it goes. And you see that the tinsel ball is strongly attracted. Once it makes contact, charge transfers fairly easily. And now they're both charged, and you can see the tinsel ball is being repelled. Right, try and get some more charge on there. So it's quite strongly repelled now. So the idea is the electrical polarization is what causes this to be attracted in the first place. And maybe I could show you a simulation so this makes more sense. All right, let's go to, where is that one? I really love this. And if you want to follow along in your workbook, we are looking at approximately page 28. Page 28. All right. Now, obviously, this simulation is not showing every single charge on the balloon and every single charge on the sweater and every single charge on the wall. But this will get you started. So for now, let's assume that is all of the charges there. We know there are millions and billions and moles more. what happens when I rub the balloon with fur or rub it on a wool sweater? What's actually happening is this. Ready? 1, 2, 3, here we go. Some of the electrons on the sweater are transferred onto the balloon. Now, if I could hold this here, what would happen is if I let go of this right now, the balloon is negative, has an excess negative charge. It would be attracted to the sweater, which has an excess positive charge. When I let go, we see it drift over there. All right? What I'm more interested in talking about at this moment is the wall. I want you to watch the charges in the wall on the right side of the screen. As I bring this, and let's get a lot of charge on here. So let's get all the negatives we can. Okay, so this is absurd, but yeah. Let's say we got a whole bunch of negative charge on the balloon. Watch the charges in the wall as I bring the balloon closer. Can you see them starting to reorient? What's happening is the plus charges in the wall are so massive they don't move much, but the electrons are trying to reorient themselves or reorganize themselves so that they're slightly farther away from this massive negative charge getting close. As a result, if I let go of the balloon right here, it actually sticks to the wall. Now, the wall is not positively charged. The wall is electrically neutral. However, we could think about the forces from each different charge here. Maybe I'll just do these in black. The force from these charges, the ones closest to the balloon, will be very strong and attractive. The force from these charges would be very strong and attractive. Then the forces from these would be moderately strong and repulsive, right? And so the idea is because the minus charges are slightly farther away, the force they attract, or sorry, the force that they would repel the balloon with is slightly smaller than the force used to attract the balloon. And if you get enough charges, these slight differences due to the reorientation of the negative charges is just enough to hold the balloon to the wall. Now think, most walls are not made of conducting materials. And so this is very weak. That's why this works only with very light objects like balloons. You don't see this polarization working with bricks or something, right? You're not going to adhere something very heavy to the wall. It's because these electrical polarization forces, they're very, very small, very weak generally. However, we did notice the tinsel ball, which is a conductor, was much more strongly attracted. All right, so I tried to discuss this on page 28. Hopefully you could maybe think about this in your own way. And what else did I want to do here? Oh yeah, if you want to go further on this, you can look at the problems on page 29, in particular 22.29 and 22.30. And I think several of the parts are really easy on those questions, at least on 22.29. But if you do all of them, you have to think about this. And so if you take the time to actually do that, you might learn something. And that's it. That's all I really wanted to say about this polarization. It's a phenomenon we see in the real world. Let me stop the share here. This is a phenomenon we see in the real world. Sometimes I ask a concept question on a test about this. And the main thing that we want to think about, just summarizing. Let's say we have an initially neutral molecule and it gets polarized. When it gets polarized, for whatever reason, maybe there was some charge nearby, one side of the object might become slightly negative, one side of the object might become slightly positive. And as a result, if you put another object near it, sometimes we can get a force. So if we put a plus charge here, well, this object that's polarized, even though it's electrically neutral, would be repelled, right? So if we had this plus charge here, this plus charge would push harder on these plus charges than it would be attracted by those minuses. And so we get this force difference. Similarly, if this was a negative charge, there would be a net attractive force because the pluses are a little bit closer than the minuses, all right? and these forces are very weak. Perhaps you've heard of these in chemistry. If you're a chemistry major, you've heard of dipole forces. And so they're very weak. Imagine two dipoles interacting with each other. Let's go even further. Let's say you had two dipoles here. So we have two charges. Both objects are electrically neutral. So both molecules are electrically neutral, but there would be a very weak attraction here. These two sets of charges, this side of this molecule and that side of that molecule would attract. These parts would repel, these parts would repel, these parts would attract. The strongest force of the four is going to be between these two because they're closest together. And so this could be used to cause a intermolecular force, but it's very weak. And yeah, so this is much less force in a chemistry bond than, say, ionic bonds, where one is positive and one is negative. So to be clear, if you just have sodium and chloride, or these are ionized, if you have some ions, this would be a very strong bond. Salt, right? Because the plus attracts the minus, and here the dipole forces would be much weaker than that. So you can read about that and discuss that more with your chemistry teacher. That's all I really wanted to say about electrical polarization.